In this video, we are going to be talking about molecular asymmetry. First of all, in the last video, we spoke about optical activity. An optically active compound can rotate the plane of the polarized light either to the right or the left. If it rotates it to the right, it's a dextrorotatory compound. When it rotates it to the left, it's a levorotatory compound. This can be identified using a polarimeter. Louis Pasteur observed that the compounds generally form mirror images. Let's take, for example, this is our compound. So the black one, B, is denoted by a straight line and A, whereas E is denoted by dotted line showing that it's going away from us, whereas D is coming towards us, so it's denoted by a solid wedge. Now its mirror image, if you notice, the mirror image of this is the A coming, like A and B is the same as it was, and so is D and E. Basically, this will be the, so this is the original one. The mirror image would be this way. Only difference is that these molecules are going to stay like, this. So what he said was that these mirror images tend to rotate the plane of the polarized light, okay, in the opposite direction. Let's take, for example, this particular compound rotates the plane of polarized light 30 degrees to the right. Then its mirror image will rotate the plane of the polarized light 30 degrees to the left. And this, so basically, the rotation is to the same extent but in the opposite direction. So this difference is because of the variation in the arrangement of the molecules, or rather variation in arrangement of the various atoms of the molecule in a three-dimensional space. This led to the most amazing, or rather a very interesting branch of chemistry called as stereochemistry. That's why we talk about how the variation in like the three-dimensional space affects the various properties and all the fun stuff that we learn. Dutch scientist Van 't Hoff and a French scientist called C. Lebel, in the same year, they independently said the following. First of all, they said that the arrangement of the carbon like molecule is in three-dimensional space is a tetrahedral shape. So tetrahedral has 3 bonds like this, and you have one upwards, and you have this having a particular angle. That's why we have been writing the various molecules of carbon in a thick and dotted wedge to show the fact that it's a tetrahedron. Not only that, they said that if the substituents are different, then the mirror images are not superimposed. So what superimposed means is that when you have like if you have an object which does not have like, now let's take this toothpick as the best example that I have over here. So toothpick, when you have its mirror image is just the same, right? So like there's no difference even between this toothpick and its mirror image. On the other hand, when we take a hand, obviously I'm not going to even try. The right and the left hand seem similar, but excuse me, they're not superimposable in nature. So they said that when you have a carbon which is attached to 4 different substituents, their mirror image are not superimposable. So I can't place this on this and it'll be the same structure. No, because of the various substituents. On the other hand, and as well as this particular carbon which is arranged to 4 different substituents is called an asymmetric carbon. Let's, for example, replace, let's take the pink one out, and if we replace it with another blue one, then this carbon automatically is not asymmetric because it is attached to 2 similar substituents. And the last one they said is that the molecule, if does not have a symmetry, then it basically is not going to be, or rather, the molecule will not have any symmetry because of the asymmetric carbon atom. And the asymmetry and the non-superimposable characteristic of a particular compound is by these molecules are becoming optically active. So from this we can basically understand that for a compound to be optically active, we have to have at least 4 different substituents attached to the carbon. Basically, we need an asymmetric carbon and they should have a non-superimposable mirror image. Only then it can be considered optically active. Not just that, we cannot also, I'd like to again remind you that we cannot say that, okay, this particular compound is going to rotate the plane of polarized light to the right or the left just by looking at the structure. We need a polarimeter to predict if it's going to rotate to the right or left and what is the angle of the rotation. Here we can just predict the fact that, okay, a molecule can rotate it because it has an asymmetric carbon, basically a carbon containing 4 different substituents, and the molecule can form like a non-superimposable mirror image. With that, we're done with molecular asymmetry. In the next video, we'll be talking in detail about optical activity.